continuing on with our discussion area. So this is the problem we just finished in the last video. And both these first two problems we did, this one and the cosine one over here, these were all just about a curve, the region being bound by the curve and the x-axis. Whether my curve be above the x-axis or below the x-axis, the region was essentially bound by the curve and the x-axis. When we're above the x-axis, it's just the definite integral. When I'm below the x-axis, it's the opposite of the definite integral. We're going to make it a little harder now. Consider the area, we got the area between two curves. Now, I'm going to explain it two ways. It's a little easier to understand it this way, which is why this one's in print, but then I'll also explain it in terms of Riemann sums. Consider the two continuous functions f of x and g of x, such that f of x is greater than or equal to g of x on some interval a to b shown below. Now, I happen to show the functions above the x-axis. They do not have to be above the x-axis. What is important is this relationship right here, that f of x is greater than or equal to g of x, that we basically have a top curve and a bottom curve. Doesn't matter where they are in relation to the x-axis, just that we have a top curve and a bottom curve. The area between f of x and g of x on AB, so we're looking to calculate this region right here. We want to know what that area is. Could be calculated as follows. Let's zoom in a little bit so you can read it a little bit better. And so that's itty bitty tiny print. Even if you have the things printed out right in front of you, it's itty bitty tiny print. But that says the area between F and G would be the area bound by F. So everything from here on down, let's see if we can get that to focus a little bit better. Yeah, that's a little better. That the area, just that blue shaded area, could be the area bound by f of x and the x-axis. So everything underneath the top curve to the x-axis minus the area bound by g of x and the x-axis. So then minus this guy right here. So the blue would be everybody underneath f, all the region underneath f. And then to get just the blue, subtract off the region between G, under G. So that's what this is saying, that I can get the blue area by taking the region underneath F and subtract off the region underneath G. Well, the area underneath F would be the integral from a to b of f of x dx, and again, in this picture, I drew it above the x-axis for informational purposes. It doesn't have to be. The formula we're going to get to works for all whether it be above the x-axis or below the x-axis. But for explaining it this way, we're keeping it above the x-axis. Then I'll explain it another way where it won't matter. But the area underneath f, the integral from a to b of f of x dx. The area underneath g, the integral from a to b of g of x dx. Those have the same limits of integration, so I can put those guys together and say the integral from a to b of f of x minus g of x dx, or very generally, the integral from a to b, top curve minus bottom curve dx. And so then we get an official definition here. If f of x and g of x are continuous, with f of x greater than or equal to g of x throughout a to b. So that is saying that f of x is the top curve. And you really don't want to memorize just general f of x minus g of x. I've had students do that. Well, it's not really f of x. It's the relationship here that's important, that f of x is the top curve, g of x is the bottom curve. But starting again, if f and g are continuous with f of x greater than or equal to g of x throughout some interval, closed interval a to b, then the area of the region between the curves y equal f of x and y equal g of x from a to b is the integral of f minus g from a to b, or that is, area equals the integral from a to b of f of x minus g of x dx. So there's a way to understand it if everything is above the x-axis. Now, why this works in general. Now, what you really need to remember is this guy right here, top curve minus bottom curve. Why this works in general. So pretend you don't even really see the x-axis there. If we think about that Riemann sum thing, and so I'm going to draw a little picture there, a little red rectangle, draw a little picture, a little red rectangle. We could call the width of that rectangle delta x. And so the area of that rectangle would be height times width. Well, we just called the height delta x, or we just called the width delta x. Zoom out so we can see this. There we go, that's better. So I've just put a little red rectangle here, and I'm just trying to explain this in terms of Riemann sums. But again, what you really need to remember is down here. So if I put a little rectangle in there, call the width of the rectangle delta x, then the height of that rectangle. Well, the height, the way you measure a vertical height is top minus bottom. So that'd be f minus g. I'm going to leave off the x's just for speed of writing. And so then the total area would be the limit as n goes to infinity of the summation from k equal 1 to n of f minus g, and leaving off the x's, blah, 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 delta x. And so it's not important at all. So I get a Riemann sum here, and so this would be the integral from a to b of f minus g dx. And so doing it this way, not important at all where the orientation, how it's related to the x-axis. That if I look at it in terms of Riemann sums, I'm just adding up all those rectangles where the height of the rectangle each time is f minus g, and then the width, delta x. Well, we remember that the limits of Riemann sums just give me definite integrals, and so there's why it doesn't matter what the relationship to the x-axis is, that if I do it in terms of a Riemann sum, the average rectangle has that width, and then when I add up all the rectangles, I get that definite integral. Now again, what you need to remember is that guy right there. So let's do some problems. Find the area bound by e to the f of x equal e to the x and g of x equal e to the 4x on the interval from natural log of 2 to natural log of 4. And like I said, you need the graphs. Do not try to do these without pictures, because just because I labeled this f and labeled this g, I'm not guaranteeing that that's on the top. I'm not. So you need the pictures. You can do anything you want to get the pictures. We're just going to do a graph here. And we'll make my calculator do it. So we've got e to the x. Remember how you can get e on the calculator. Second natural log. I didn't get second there. Second natural log gives me e, and I just want x. And then e second natural log to the 4x. Now here's a little trick. If you want to be able to distinguish the two curves so they don't look the same on your calculator, arrow back until you get to that little diagonal line there. And see how that diagonal line is now flashing? If I hit enter, it's now flashing with a thick line. And so what it's going to do is it's going to graph e to the 4x with a thick line and e to the x with kind of the ordinary line. So if you're not sure which curve is going to be which, you can use that little trick. And what I did again was I just arrowed all the way back to that diagonal line, and then you hit enter. And if you hit enter a couple times, there it's going to do some sort of weird shading. There it's going to do some sort of weird shading. I'm not really sure what it does with that one. I'm not sure what it does there. Now, and I think that's a dotted line that it's going to do. I'm just pressing enter each time. There's the normal line, and there's the thick line. And then, since we don't know any better, just hit zoom 6. And there's the e to the x graph, and there's the e to the 4x graph. So just roughly copying it onto my paper, they are both going through 0, 1. And so I'm going to say this is the e to the x graph. That was the lower one, so to speak. And how about green? And that's the g of x equal e to the 4x, the fatter line. And so there's the graph. And then it says from the natural log of 2 to the natural log of 4. Just to get some sort of idea, natural log of 2 is roughly 0.69. So let's call that 1. And natural log of 4 is roughly 1.3, so let's call that 2. And so we're looking at roughly this region in here. I'm going to have to adjust my graph a little bit. It doesn't want to work for me. There we go. I'm just going to adjust this a little bit so the graph's a little prettier. There we go. And so this was about 1.38. So here we said that's the natural log of 2. And we'll call that the natural log of 4. And so there's the region I'm looking at. You need to get the region. So now that we have the region, and you'll see a lot of people do this. They will draw a little rectangle in there to represent the idea that it is Riemann sums, and it really is Riemann sums. The limits of Riemann sums give us definite integral. And that just helps some people. I know yellow was not the best color to pick there. And so my area, in general, from A to B, top minus bottom, dx, in this case, it's going to be the natural log of 2 to the natural log of 4, because they gave us those values. The top curve in this case is e to the 4x. That's where the top of the rectangle is. Minus the bottom. The bottom of the rectangle is e to the x dx. And there's the integral that's going to do it for us. And now we integrate. E repeats itself. Then the effect of that 4, if I was differentiating, I would multiply, chain rule. But I'm anti-differentiating, so I divide by that 4. And again, the integral and the derivative of e to the x is e to the x. Evaluated from the natural log of 2 to the natural log of 4. And then do my evaluation. And again, I prefer to work term by term. So plug in the upper limit, plug in the lower limit, and subtract. And again, this is not, let's put it this way, do not do this. E to the 4 times natural log of 4 minus natural log of 2. Some people will do that they'll keep, I'll put the 1/4 out in front too. They'll keep the 1/4, they'll keep the e, and they'll keep the 4, and then they only think about plugging into the x, upper minus lower. You're plugging into the entire function. You're taking that natural log of 4, plugging into the entire function, plugging in the natural log of 2 into the entire function. Then minus parentheses, e to the natural log of 4 minus e to the natural log of 2. And now we start to simplify this, and we do want it fully simplified. Recall, the natural log, let's put it the other way around. E to the natural log of x is x, and p times the natural log of r is natural log of p to the r. So simplifying this, on that first guy, those two coefficients of 4 can come up and become coefficients on the arguments of logarithm. On the second guy, I've got my rule there. E to the natural log of 4 is 4. E to the natural log of 2 is 2. And so now I have 1/4 times 4 squared, 4 to the 4th, excuse me. 4 to the 4th minus 2 to the 4th. Then minus 2, And then whatever it works out to be there, I'm almost out of time, so we'll leave it at that.